Okay.
Again, and I have to loosen this so I can move it.
Okay. So the periodic table is split up into 4 parts. You have the SPD and F blocks. And so the S blocks are going to be over here on the left side of the periodic table. Then you're going to have your D blocks in the middle, transition metals. Then you're going to have your P blocks on the other side. And then the lanthanoids and the actinoids are going to be your F blocks. Alright, so you have your alkali metals. That's groups 1 and 2. Then you have your halogens, and that's group 17. Noble gases, group 18, of course. Transition metals, 3 through 12. Then you have your lanthanides and actinides, and they're separate. And they're in period 6 and 7.
Well, the lanthanides specifically fall between atomic numbers 57 and 71. And the actinides specifically fall between the atomic numbers 89 and 103. But if you look at the atomic periodic table thing that's there, it'll show you how it's specifically split from the actual periodic table. Groups are numbered 1 through 18, 1 being where the alkali earth metals lie, and 18 being where the noble gases lie.
So groups 1 through 2 are the S blocks, right here. And then the P blocks are 3 through 12, transition metals, right along here. And then you have your P blocks, which are 13 through 18, over about this distance. And then the F blocks are still the lanthanoids and actinoids. Okay, so the different groups on the periodic table show the number of valence electrons it has. So going from left to right, the valence electrons are going to increase as you go across the periodic table. So another thing the groups tell is that it tells as you go left from right, the pattern of the electron configuration increases. So it starts out with 1 and then it keeps going until you get to the other side, like that. And as you move down the periods, the electron configuration also gets bigger. And so the noble gases on this side, over here, they act as a check mark because their valence electrons are filled. Also in the same periods, all the elements in that specific period share the same chemical properties. So like if this was period 2 per se, all these elements are going to share the same behavior chemically. For the atomic radius, it's going to decrease as you go across the periodic table from left to right. But it also increases as you go down the periodic table. The atomic radius. So, for this we have the radius of a circle, obviously to figure it out. Distance from the center of the circle to the point on the circumference, called RC. Then we have, so this occurs, it decreases across the periodic table because of the increasing effective nuclear charge. And the atomic radii increase down the periodic table, obviously. And the increasing charge pulls the valence electrons closer to the nucleus. For ionization energy, it's going to increase as you go across the periodic table, and it's going to increase as you go down the periodic table. Shabam.
Now the ionic radius. The radii of cations and anions differ from the parent atoms for which they are formed. The radii of cations are smaller than those of their parent atoms because they are more protons than electrons in the cation, so valence electrons are more strongly attracted to the nucleus. The radii of anions are larger than those of their parent atoms because the extra electron in the anion results in greater repulsion between the valence electrons.
Now, when we talk about ionization energy, we mean the minimum energy required to remove an electron from a neutral atom in its ground state. Now, it's only measured in the gaseous state. That is important. Remember that, okay? Good. I mean, to you. Alright, the first ionization energy decreases down the periodic table, as we covered. The second ionization energy represents the removal of another electron, so one more, as well as the third ionization energy. So each time it's adding another electron. And then the ionization values are always positive
because there's always an input of energy used to remove an electron.
So electronegativity increases as you go across the periodic table and decreases as you go down. For ionization energy, it's going to decrease as you go across the periodic table, and then it's going to increase as you go down.
Now, when we talk about electron affinity, it decreases or increases across a period depending on the electric. No, I was right. The electronic configuration, or the electron configuration.
It's in your coffee, Jim.
Vodka.
There you have it.
Since a half-filled p subshell is more stable, carbon has a greater affinity for an electron than nitrogen. Obviously, the halogens, which are one electron away from the noble gas electron configuration, have high affinities for electrons. So, the common rule that you need to remember is that more negative energy is equal to a greater affinity.
Interesting. All right, for electronegativity, don't get it confused with affinity, because they all sound the same. I'm not racist, just saying. Trend-wise, as one moves from left to right across the periodic table, the electronegativity increases. This is because of the stronger attraction that the atoms obtain as the nuclear charge increases.
Now we move on to metallic and non-metallic behavior.
My favorite.
So, metals have a high melting point. Characteristics decrease from left to right because of the attraction between the valence electron and the nucleus is weaker. Characteristics increase as you move down the periodic table because electron shielding causes the atomic radius to increase, thus the outer electrons ionize more readily. Now, all of this pertains to the melting of metals. Metallic character relates to the ability to lose or gain electrons.
As for nonmetals, it applies to the ability to gain electrons. Total opposite. Also, nonmetals have a low melting point. Very different. Now, for oxides, they vary between acid-base and amphoteric due to the fact that they acquire anhydrides, which change the characteristics depending on the amount of water added. So, less water equals more acidic. More water, more basic. Bam. That's why it's amphoteric, because it's both acid and a base. Shabam.
Now, for ionization, this is pretty simple, just a little side note, but across a group, first ionization energy decreases, but as you move across a period, it increases.
Alright, so the alkali metals are group 1, and they have one valence electron. Now, if they react with water, then they'll create a metal hydroxide. Also, the electron configuration is unstable. Like that. And this causes combustion when it reacts with water. So take lithium, for example. If we react lithium with H2O, then it'll create Li2O plus H2. But it releases hydrogen gas by itself. So therefore it's an exothermic reaction, and it releases heat, so basically the hydrogen catches on fire. That's why it's unstable.
Explosion.
Bam.
Boom.
Like this, but like...
Group trends and reactions. Alkali metals with water become more reactive down a group with water. It's confusing, but you know, whatever. In the outermost S shell of the alkali metal, they have one electron. By losing that electron, the alkali metals get the stable electron configuration.
Take your time.
In the case of halogens, they are electron short in the outermost shell, the p shell. Adding an electron, it creates a stable electronic configuration. As you move from lithium to francium, the electrons are further more away from the nucleus. Hence, it is easy to remove an electron from the outermost shell.
So what you have to remember is you have your Fn elements. Okay, you have francium and you have fluorine, right? And so they're at the opposite sides of the periodic table. So they're most easy. They react the easiest. All right.
Well said. Oh, and we also have to give rights to the Fn elements. It's a trademark of Mr. Matt Chase. He's promised us an A if we, advertise his new
Yeah.
memorization product.
A for actinium.
A for
Anyway.
A for A.
Yes. So if you have a halogen and a halide, all you need to know is that it's going to create a less reactive halogen, and it's a single replacement, so they just replace each other.
Did we just stop now?
Yeah, just stop.
Dun-dun-dun, dun-dun-dun. Wait. Dun-dun-dun.
This is brought to you by McDonald's. This just in, aluminum oxide. Basic, acidic, or both? Ah, it's both. Why? It's called amphoteric. Because, alright, aluminum is close to oxygen. So, it is an ionic bond because aluminum is a metal, so it creates a metal oxide. But they both share the same characteristics. It's an ionic bond with covalent characteristics. Silicon dioxide doesn't dissolve in water. Why? Because it's acidic. But because it reacts with sodium hydroxide. Bam!